Well, good morning. Happy Wednesday to you. Hopefully you guys get a chance to get outside. Looks like it's going to be another beautiful day today. We're going to make things fairly easy on you today. We're just going to talk about kind of where we can go with this whole idea of momentum, because a lot of the stuff we've been talking about in class, they had already kind of figured out all this pretty much by the middle of the 1700s. So we're not exactly high tech with the stuff we're doing. We're rolling stuff down ramps, we're pulling carts, but some discoveries came along that really kind of challenged the way we thought about how the world worked. And so that leads us into kind of the idea of quantum physics here. And one of these things that kind of caused us to make this quantum leap, I'm really misusing that term there, is the discovery that light is the ultimate speed limit of the universe, okay? So if light travels at 300 million meters per second in a vacuum, okay, it doesn't matter what your frame of reference is, everyone is going to observe the same speed of light. Doesn't matter if you're stationary, if you're moving, you will always perceive that light to be moving at 300 million meters per second. Now, this might not seem to be that big of a deal, but one of the things that happens from this is, let's say you've got a train that goes to the right here. Let's say that it goes at an exceptionally high speed, okay, somewhere near the speed of light. If I'm an observer in this train, if I'm in this train and I shine a flashlight, it's going to hit a mirror and then bounce back at me, and that's what it looks like, and that's what's happening. So my velocity within that train of that speed of light is going to be d over t, and the velocity of light we are going to represent with the letter c. Okay, not too big of a deal. But let's say you've got an observer on the side of the train who's going to observe exactly the same speed of light, but the observer on the side of the train watches this light follow this path. Because this train is moving so fast, now this light follows this path. And so its distance, let's say, is twice as long as it would be just going back and forth here. But the same speed of light has been observed by this observer. What that means is that if that's the case, that means that my time has doubled. Okay, so time is relative. Time depends upon how fast you are moving, which is kind of a curious concept, but this might just seem a hypothetical, but has been shown to work out again and again and again. So as Einstein came to understand the idea of relativity, he realized that our classic equation for energy wasn't complete. Now, one of the ideas we're going to explore when you guys return in January is the idea that kinetic energy equals 1/2 times mass times velocity squared, which looks kind of similar to our idea of momentum. With energy, velocity plays a little bit more of a role, but you see here that there's some type of relationship between these two. But we're going to see how, when we tease this out, that there's going to be a separation of these ideas. So Einstein thought that momentum had to be conserved, that whatever happens in the universe, we have to conserve momentum. So let's say we've got a fast-moving object, and I know that a change in momentum is going to be described by this impulse, force times time. What happens if I keep applying a force over time, especially as I near the speed of light? Let's say I got a spaceship going uber fast, okay, but I keep applying a force to it. Because I can do that, okay, we know that F equals ma, okay, I can keep applying a force, and if I keep applying a force, we'd keep expecting an acceleration. But the problem is that as you approach that velocity, as it approaches the speed of light, now it becomes tougher and tougher to accelerate, even if I introduce more energy to it, even if I keep applying that force. So if that's our idea, we've got a problem here, because I can keep applying a force, but at some point I can no longer accelerate this object. Seems like we have reached an impasse. Now, since c, which is the speed of light, can't be reached, I can't go faster than the speed of light, okay? Does that mean that there's an upper limit to an object's momentum? That if this is our description for momentum, is the upper limit of an object's momentum p equals mc, where c equals the speed of light? Is there a limit? Can I have a limit on my momentum? Well, Einstein thought, no, you don't have a limit on momentum because you're still applying a force to it, okay? But he thought we needed a new equation for momentum. This is the equation for relativistic momentum. Now, it might seem a little bit complicated, but you're going to see that really at velocities which are low compared to the speed of light, this simply simplifies down to p equals mv, which is what we were taught. So basically, if the speed of light is 3 times 10 to the 8th meters per second, and my velocity is, let's say, 5 meters per second, 1 minus 0 is basically 0, or 1 minus 0 is basically 1. Take the square root of 1, it's 1. Okay, so p would basically equal mass times velocity if I'm traveling at relatively low speeds compared to the speed of light. But as this v gets higher and higher, once I start approaching the speed of light, you're going to see that this is going to have an impact on this value, okay? On this overall value, I should say. So near the speed of light, this momentum begins to increase significantly as a result. And since I cannot exceed the speed of light with this velocity here, that means that the only way that we can remedy this, it means that the mass of the object must increase. Which seems kind of bizarre. It doesn't seem like, hey, this object near the speed of light is going to eat a couple pizzas and gain mass. It gains what's called inertial mass. It's tougher and tougher to accelerate. And again, this seems a bizarre result of this idea, but as I approach the speed of light, an object will gain mass because it becomes more and more difficult to accelerate an object. And basically, that's the definition of mass. The resistance to an acceleration is inertia. Inertia is based upon mass. So, but one other side step of this is that it means that objects have energy even when they're at rest. Even when they're at rest, it would imply that an object has what's called rest energy. And if our equation for kinetic energy is 1/2 mv squared, rest energy can be described as E equals mc squared, where my guess is that you've seen this equation before, but this had rather startling implications. And it's because of this that we now understand how stars work, how the atoms work, how we actually derive a third of our energy in this state is because of this equation here. And the ramification of this is that this implies that even if an object's at rest, it has energy, and this energy can be described as E equals mc squared, where m is mass, c is the speed of light squared. And if the speed of light is 3 times 10 to the 8th meters per second, you can see that if you square that, you're at 9 times 10 to the 16th meters squared per second squared. That ends up being a pretty big number. So that means you don't need a lot of mass to create a lot of energy. So mass can be churned into energy. I can convert mass into energy, and that's what happens in the processes of fusion and fission. In fission, you have a larger particle break apart, and in this process, some of the binding energy that is used to hold that together is released in the form of energy. In the process of fusion, the same thing happens. We have particles coming together, making a larger particle in the process of fusion, but in that process, mass is lost, but is converted into energy. Now, the reverse of this is that if mass can be turned into energy, energy can also be turned into mass. And this is the premise behind the Big Bang. We had a singularity which had just an unbelievable amount of energy, and that energy was kind of reverse ordered into mass. It's a kind of a symmetrical idea here. One can turn into the other, and one can turn back again. But the world gets crazier still. All matter that's out there, doesn't matter if it's an electron, a proton, a bird, you, me, all matter has a wavelength. And we're going to talk about waves second semester, but we're going to use this symbol for wavelength. It's called lambda, Greek letter lambda. And this wavelength can be described by this formula, where lambda equals h divided by p, and we know that p is my equation for momentum. And h is a variable, not a variable, a constant. It's called Planck's constant. And it is the equivalent of 6.63 times 10 to the negative 34th joule seconds. And this has a very small number here. So you can see that for large objects, it's difficult to see a wavelength. For something that you and I, who have, let's say, 60, 70 kilograms of mass, okay, that's going to be a situation where this mass times this velocity, this is going to be a relatively large number, and that's still going to be a small number. So that wavelength would be far too small for us to notice. But if you start getting down to objects like electrons, they display attributes of waves just like light does, okay? Which leads us to the idea of the wave-particle duality of nature. All objects have both a particle function and a wave function. And because of this, because we can treat electrons like waves, okay, it's actually a very, very short wavelength. So we can use the wave features of an electron to actually treat it like light. And this is the basis behind electron microscopy, where you can get incredibly high resolutions of very, very small objects at these incredibly short wavelengths. So it's because of this idea that there's a wave-particle duality. Everything has a wavelength which can be described by that formula. Now finally, you may have heard of a term called the Heisenberg uncertainty principle, which means that both the position and the velocity of an object can never be known at the same time. Because if I multiply my uncertainty in my position times my uncertainty in my momentum, that is always going to be greater than this right here, which ends up being Planck's constant divided by 2 pi. So, and the problem is that if I try to measure the momentum or the location of an object, I have to use light in order to do it. And that light is going to knock that particle away. So I'll have a high uncertainty in my momentum, even if I know my position very well. Or conversely, if I try to measure my my momentum really well, I'll know my position less. The more I know of one, the less I know of the other. And so this means that there's always going to be a little bit of an uncertainty about where an object is and how fast it's going, and kind of that whole idea of momentum and its position. I'm just not going to know it all. So there's a video here that's also attached to your assignment for today. Your assignment is actually no assignment. Okay, I just wanted to inform you a little bit about some of the ideas that are larger ideas that we probably won't get to this year, and just kind of edify you and make you a little bit wiser about how the world around you works. So you will have a test Friday. The people who are in the B cohort in distance, you have a couple labs to finish up tomorrow. The A cohort, your job tomorrow is going to be simply to study for the test, and everyone's going to take the test on Friday. If you could, there's a second video here I would ask that you watch that describes Heisenberg's uncertainty principle, and then we will call it a day. Hope you guys have a good one. We will see you tomorrow.